Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, good morning, everyone. Sorry, there's a sudden change of location. So for those who watch online, we basically moved to the Cume Theater. So that's why there's about like 10 minutes delay. Okay, so at the beginning of the workshop, I'd like to announce that quiz 4. So for your quiz next week, you will be on the futures options. Okay. So for quiz next week, it will be based on this week's content. Futures options, all right? Okay, so let's get to it. So in today's workshop, mainly it's all about applications of Black-Scholes pricing model to the futures options. And also we're going to talk about how we modify the binomial pricing approach and how we're going to use the binomial approach to value the futures option. So the first question says, suppose the 7 months futures price on gold is currently 950 per ounce. Volatility of this futures contract is expected to be 40% per annum continuously compounded. The risk-free rate is 6% continuously compounded. And the question says, using above information to calculate the price of a 7 months European put futures option on gold with a strike price of 1,000 per ounce. Okay, so in Monday's lecture, we'll talk about the modification with Black-Scholes model is first with the preliminary calculation. When we calculate D1 and D2, the first thing we do is we replace all the spot price, which is S0, with your futures price F0, right? So that's the one thing we're doing here. And the second modification is that we talked about the futures price is really just like a stock price, just like a stock price that pays a dividend yield equal to the risk-free rate, right? And the last week, we know how to deal with the underlying asset that pays the dividend yield. All we did with D1 is simply subtract the dividend yield Q from the risk-free rate, correct? And that's one thing we did. So basically, last week, on this right-hand side of the bracket, we have R minus Q plus the variance term divided by 2, then times the time to horizon T. But today we talked about because the future price behaves like a stock that pays a stock dividends that equal to the risk-free R. So basically what we have on the right-hand side is R minus R, so we're getting a 0 on the right-hand side of the bracket. Well, that just made our life so much easier. So what we have in this equation is we have the natural log of your futures price divided by the strike price plus the variance, so variance times the time to horizon divided by 2, and in the denominator is simply sigma times square root of time t. Okay, we were told the future price is 950, strike price is $1,000 an ounce, plus the variance, so that's 40% square, times time to maturity is 7/12 divided by 2. Okay, so in the denominator we have the standard deviation 0.4 times square root of 7/12. Okay, so we get the D1 value, then we run up to 2 decimal places. Okay, so as I mentioned in the last week lecture, a lot of people email me says, Mars, how many decimal places to keep for D1 calculation? Well, when it comes to finding the probability, keep to 2 decimal places. Okay, so do not try to use the interpolation method. I know some people know how to use the interpolation method to interpolate up to 4 decimal places, then find a more accurate probability. Now, in this course, all you need to do is keep to 2 decimal places. But when it comes to the sequential calculation for D2, so when I say sequential calculation, I mean using the D1 value, plug into the D2 equation. When it comes to that, keep as many decimal places as you can, okay? So that's what I did. I keep as many decimal places as I can, plug into the D2 equation, I get the D2 value is minus 0.02. Okay, so going back to the question, we were asked to calculate the price for this put futures option, right? So we know in the put option equation, we're really interested in n minus D1 and n minus D2, right? So in other words, we need to put a minus sign in front of D1 and a D2. So in other words, what we really need to find is positive 0.02 and positive 0.32. Okay, so let's go to our table. 0.02 here corresponding to our probability 50.80, and positive 0.32 corresponding to the probability of 62.55. All right, so we quickly write down there. And then, so this is the formula for the put option. Now, the only modification with the put option is we change the spot price with the futures price, and then we discount this futures price back to the present. And also in the original put option formula, we also have this present value of the strike price, right? Now, since we have both e to the power of minus RT in the equation, we can single out that e to the power of minus RT outside of this square bracket. Okay, so next thing you know is we're discounting the strike price times this probability minus the future price times the probability associated with n minus d1. We're discounting this whole component back 7 months at a risk-free rate, and we find that the price of this European put futures option written on gold should be selling for $100.37.99. Okay, so quite straightforward. Just two modifications. One is the one with the D1, and another one is the one with the spot price here in this final equation. Okay, so the next question is about calculating the price for the coal futures option. Basically, the logic is the same. So we were told that suppose the 7 months futures price on gold is currently $950 per ounce, and the volatility of this futures contract is expected to be 40% continuously compounded. Risk-free rate of interest is 6% continuously compounded. Using above information to calculate this 7 months European coal futures option that written on gold with strike price of $900 per ounce. Okay, so D1 and D2 formulas are identical to the previous slide. So basically, we know what the future price is, 950, and the strike price in the second part of the question, so in this question here, is $900 per ounce. Okay, and so the variance is still 0.4 square times 7 over 12 divided by 2. Then in the denominator, we have 0.4 times square root of 7 over 12. So we're getting this D1 value. Then again, we plug this D1 value into the D2 equation. We get the D2 value, keep it to 2 decimal places, is 0.02. Okay? And then we go to this set of table. So when it comes to positive value, we go to the table, indicates the value is positive. So D1 is 0.33. It's associated with a probability of 62.93. And the D2 value is 0.02. So that is associated with probability of 0.5080. Okay, so similar to the put option formula, the only modification we've done with the call option formula is we replace the spot price with the futures price, and then we're discounting that future price back to the present. We know what the future price is, 950. That times the probability associated with ND1 and subtract the strike price times the probability associated with ND2. Okay, we discount back 7 months. We get the coal futures option price is priced at 135.80 cents. So the first two questions is quite straightforward. Straight up application of the Black-Scholes formula for the futures option. Okay, so part C of the first example says, again, suppose 7 months futures price on gold is currently priced at $950 per ounce. The volatility of this futures contract is expected to be 40% per annum, continuously compounded, and in addition to that, the risk-free rate is 6% per annum. Using above information to calculate the bonds for at-money 7 months American call futures option on gold when a 7 months American put futures option on gold with the same strike price, and we were told this American put is selling for $48. Okay, so let's think about how to get the bonds for this American call option. So what we were told is we know the futures price, right? So futures price is 950. And also, we were told the risk-free rate. What else we were told? We're told there's a call option and there's a put option. They have the same maturity and the same strike price. And luckily, we already know the price for this put futures option is 48. So that reminds us of the put-call parity, right? So this is the perfect scenario for using the put-call parity because we have a call option, we have a put option. They have same maturity with the same strike price. And also we have other inputs for the American put-call parity. So here is the put-call parity for the American futures option. And we know what the put option is selling for. The put option is selling for 48, right? And in the question, we were told the futures price, and we know what the strike price is. So the futures price is 950. So 950 discount back 7 months minus the strike price 950. We don't know what the call option is, so we keep that as unknown. However, we do know that this put futures option is selling for 48, right? And the future price is 950 minus the present value of the strike. Now, once we plug those variables into this equation, we're only left with this one unknown variable. Then just matter of rearrangement, we get the boundaries for the call option. So this call option should not be selling lower than $15.32, should not be selling higher than $80.67. So basically, we just use the American put-call parity formula to get the bonds on this call futures option. And the rationale is that we were given a call, we were given a put, and it just so happened that this call and put have identical maturity and have same strike price. So that's the perfect scenario for us to apply the put-call parity formula. So any question on this? Any question on the part C of the first example? Okay, so in Monday's lecture, I only talked about what kind of changes that is made to the binomial option pricing approach dealing with futures option, but I did not show you how to do that with the numerical example. So here we have one question says, a futures price is currently 60, its volatility is 30%, risk-free rate is 8% per annum, and we were told using a two-step binomial tree to calculate the value of a 6-month European put option on futures with a strike price of 60. If the put option were American option, would ever be worth to exercise the early? Okay, so I've received email like this, says, Mars, when I receive a question, I don't know whether I need to use the Black-Scholes formula or use the binomial approach. So basically, we know that the Black-Scholes formula can only be applied to European options, right? However, the binomial can be applied to both European and American. So when you receive a question that tells you it's a European option, it's tempted to use binomial approach. However, one way that to distinguish whether to use the binomial or Black-Scholes is to read the question carefully. If you were not told how many steps you need to set up your binomial tree, then chances are you need to use the Black-Scholes formula if the question tells you this is a European option. Does that make sense? So let me say this again. So a lot of students, when they receive question, if the question is about a European option, they were confused whether to use binomial or Black-Scholes. Well, the simple way to tell that is by reading the question, see how many steps that you need to build up the tree. If you are not given this information, the chances are you need to use the Black-Scholes formula, right? Because if you were not told about a step, then it's very arbitrary. You know, somebody can use 3 steps, other people can use 2 steps. So, so just read the question carefully, okay? See whether you were given this information. So in this question, we were given the information that we need to use a 2-step binomial tree to calculate this 6-month European put option. Okay? So the first step is to calculate our proportional increase and proportional decrease. By the way, you need to memorize this formula for calculating the proportional increase, the little u. So this formula will not be given in the final exam. So basically, the proportional increase is simply e to the power of sigma times square root of delta t. So we were told the standard deviation is 0.3. And delta t, so what is the delta t? Delta t is the length of 1 step, right? So basically, this is a 6 months put option, and we split into 2 steps. So that's 6 months. So that's 3 months per step. So that's 3 over 12, right? We get the proportional increase is 1.16, and 1 over that is the proportional decrease. So that's the first step. Then the second step, having the little u and the little d, we can draw our tree, right? And we were told the future price starts at $60. So $60 multiplied by the proportional increase, 1.16, we get to a future price up here, $69.71. Okay? Then we take this future price multiplied by the proportional decrease, 0.86. We get a future price down here, 51.64, right? And you know the rest. Basically, just repeat the same step to complete this binomial tree. Okay? So the rest is quite mechanical. So once we get this entire binomial tree, as I mentioned, you should quickly work out the payoff for this put option at each terminal points, right? So we have 3 terminal points. Remember, this is a put option with strike price of 60, right? So when the future price finish up here, $80.99, that's greater than your strike price. So clearly, the put option is out of money in this point, right? So this is out of money put. The put option has a value of 0. And when the future price finish in the middle, $60, it's not greater than our strike price 60, right? So again, we should not exercise this put option. This put option has a value of 0. However, when the future price took 2 consecutive downturn, finish here, 44.45, we have a dip in the money put, right? So the payoff is simply $60 minus 44.45. We get the payoff from this put option is $15.55. Okay? And what else do we know? We were told this is a European option, right? So the nice thing with European option is that all the cash flow happen at the terminal point. So then what we can do is we can work out the expected payoff at terminal point. Then we're discounting all the way back 6 months, right? So we don't have to work tediously from the right-hand side to the left-hand side, okay? Now to work out the expected payoff, we need to find out the risk-neutral probability. Okay, so again, we need to make some changes to the risk-neutral probability, our P star. So last week, when we're dealing with the option return on stock that pays a dividend yield, all we did is e to the power of risk-free rate minus Q, then times the delta T, remember? So as I mentioned, in the Monday's lecture, when we're dealing with the futures option, we simply set the dividend yield Q equal to the risk-free rate. So what we have here is we have e to the power of R minus R times delta T, right? So R minus R give us 0. So basically, e to the power of 0 is simply 1, okay? Then our risk-neutral probability equation become like this. In the numerator, we have 1 minus D divided by U minus D, So I would say this is the simplest risk-neutral probability formula. So in an exam situation, if you want to get a binomial option pricing question, you wish you can get one with the futures option because the P-star equation is really easy to remember, right? So 1 minus D, we know what the D is, so 1 minus 0.86, divided by the difference between U and D, we get the risk-neutral probability, which is the probability that the future price going up, is 46.26. All right, so 1 minus that gives us the probability that the future price going down, which is 53.74. Okay, and we know that all the action happen at terminal points. We can just simply work out expect payoff at the maturity, then discount back 6 months. Okay, so this tree is very simple because at this point, the put option has a value of 0. At this point, the put option has a value of 0. Now, if you discount that back here, that would just give you a 0, right? And also, so in other words, we don't have to worry about this branch here. All we need to worry about is this branch here, right? And we know how to get to that point, which is to take 2 consecutive downturns, which is for future price to going down here, then going down again. So the path probability of getting to 44 and 45 is this probability, so 53.74 times 53.74, right? So that basically just 0.5374 squared times the payoff when this happens. So the payoff is $15.55. So that's the expected payoff from this European put futures option. Then we discount all the way back 6 months at a risk-free rate 8%. So we get this European put option is priced at $4.32. So quite straightforward. So the only difference is the risk-neutral probability. Then the rest is identical to what you learned in week 5. But then the second part of the question says, what if this put option is American one? So how do we price the American put futures option? Okay, so with American put option, we have no choice but to work tediously from the right-hand side to the left-hand side. And at each knot, we need to check whether or not it's optimal to exercise early, right? Now, if it's optimal to exercise early, instead of writing down the discounted value for this put option, well, what do we need to do? We need to write down the intrinsic value of the put option, right? So intrinsic value of the put option is simply the strike price X minus the future price FT. So let's check. So basically, again, because at this branch, we end up with a put option has 0 value here and a 0 value here. So we don't worry about this upper right branch. So we just focus on the lower right branch first. Okay? So we know there is 53.74% chance the future price going down. When it's going down, we have a future price of $44.45. And then we have a put option with payoff of $15.55. So we discount back 3 months, right? Because this time we work at each branch of the tree. So we discount that payoff back 3 months. We get a discounted value of $8.19. So, but that's just the discounted value. As I mentioned before, we need to check whether or not it's optimal to exercise this put option early at knot C, right? So the way we're going to check that is by computing the intrinsic value, which is the strike price minus the futures price. So we have the strike price $60. So 60 minus the future price in knot C, which is 51.64. It gives us the intrinsic value of $8.36. So instead of writing down the discounted value $8.19, we write down this intrinsic value $8.36. So the way we interpret this is that by holding on to this put futures option another 3 months will not give us higher payoff. Therefore, we are better off by exercising this put futures option today and then make a payoff of $8.36. Okay, so we exercise this put option now. So I wrote there, so that's the payoff for the puts in Knot C. Then the next thing you'll know is to discount everything back to Knot A, back to the present. Okay, again, because we have a put option with value of nothing here, we just need to worry about the probability of going down. So we have 53.74% chance the futures price going down. Then we're going to end up with a payoff of $8.36. Okay, then we discount back 3 months. We get this American put futures option should be priced at $4.40. And you'll notice that for the same put option, if it's American, is slightly more expensive than its European counterpart, right? So the American put option is $4.40. The European is $4.32. I mean, it makes sense because American option give you all the features that European option give to you. And what's more is that you have the flexibility to access early. So that additional flexibility is worth something, okay? So any question with example number 2, which is application of binomial pricing to the futures option? Okay, again, so let's do another question with Black-Scholes, but this time, the underlying asset is a futures contract written on stock, okay? So here it says the futures price on one BHP share is 42. So 42 is not BHP share price. Rather, is the future price, is the futures price on the contract, futures contract written on BHP. And the question also tells us the risk-free rate is 4.5% continuously compounded. A 5-month American coal futures option with a strike price of 39 on PHP is currently selling for $7. Okay, again, we will ask to calculate the bonds for the price of a 5-month American put futures option on BHP with a strike price of 39. So again, when you see ask us to calculate the bonds, and one thing you notice is that for this call and put, they have same time to maturity, 5 months, right? And once again, they have same strike price, $39. And we were told, this time we were told the coal futures option price selling for $7. So, and also we know what the future price is, we know what the risk-free is, so we can kind of work out the American put future options, lower bound and upper bound, right? So we were told the future price is 42. So 42 discount back to the present, discount back 5 months minus the strike price. Strike price is both 39 for this American coal and American put. So in this question, we were told the coal is selling for $7. So the put is the unknown parameter this time. And the future price is 42 minus the present value of the strike. So again, just matter of rearrangement of this equation, we'll get to this expression here. Basically says the put option should not be selling lower than $3.28, should not be selling higher than $4.78. Right? Which is quite similar to the first example we've done. So any question on this one? Nope. Okay, so let's have a look at the part B. So the part B says you've decided to purchase a 11-month European put futures option on Rio Tinto. The risk-free rate is 4% per annum, semi-annual compounding. The future price is 57. Its volatility is 20% per annum, continuously compounded. Strike price is $60. So what is the price of this 11 months European put futures option? So again, we need to calculate D1 and D2. But before we do that, one thing you notice is that the risk-free rate is compounded semi-annually, right? So the first thing you need to do is convert that 4% into a continuously compounded risk-free rate. So we apply this formula, so that's compounded twice in a year. So that's 2 times the natural log of 1 plus 4% divided by 2. So that's 2% every 6 months. We get the continuous version is 3.96% per annum. Okay? Then again, we do the preliminary calculation for D1 and D2. We know the future price is $57 divided by the strike price 60 plus the variance 20% squared times 11 over 12 divided by 2. All right, so in the denominator is simply 0.2 times the square root of 11 over 12. We get the D1 value. Then we plug into the D2 equation. We work out the D2 value. So again, because this is a put option, so what we're really interested to find is N minus D1 and N minus D2. So what we really need to find is positive 0.17 and positive 0.36. So we find the corresponding probability for N minus D1 and N minus D2 in this table here. And next thing we know is just to plug everything into the put futures option formula. So the strike price is 60 times the corresponding probability for N minus D2, 64.06, minus the future price 57 times the corresponding probability for N minus D1, which is 56.75. Then discounted back 11 months using the continuously compounded risk-free rate. So we get the put futures option is priced at $5.87. Okay? So once again, I'd like to emphasize the next week quiz is based on the futures option. Okay? So please revise both the lecture as well as the workshop. So any question about today's workshop? I apologize for this change of location. I promise if there's another change of location, I'll make an announcement in advance, okay? I apologize for that. Thanks, everyone. Okay, I'll send to you. I do have the file. I'll send to you.
Yes, and maybe today I will send an email and let you know me by
Okay, yeah, no worries. Yeah.